In this lesson, we're going to look at different applications of geometric series or the geometric series formula. So we already did some word problems in the last lesson, and this one is just going to be other examples. We have our formula here. Just as a reminder, and it'll become especially important in this lesson, we are calling our common ratio B. So I'm going to use a B in these two spots. So that's our multiplier, our base, if we think about an exponential function. This one says a ball is dropped from a height of 32 feet. So it bounces and it rebounds 80% of its height from which it was falling. And then it kind of continues along that pattern. So we're asking what is the total downward distance it's traveled by the time we get to the 12th bounce. So kind of adding those red distances together. So we see this as a sum. We're not trying to find how far it falls on the 12th bounce. That would be a sub 12. We're trying to find the sum of all distances it's fallen. So that's S sub 12. Looking at our variables, we just said that the n value is 12. We're starting with 32. So the first time it falls 32 feet. So that's a sub 1. And this one, they actually give me the base. It's 80%. If we were in that exponential unit, we could have said the amount it bounces or the amount it falls decreases 20% each time. They just directly said that it rebounds 80% of its height. So now we're going to plug it into the formula. We are finding S sub 12 because that's the value of n. 32 minus 32 times r to the n, so r to the 12th, b to the 12th. We changed it to b, so 1 minus 0.80 for 1 minus b on the bottom. Every once in a while I still say r because I'm used to saying it that way, but it is really tricky. So we're going to have a different r in this lesson that will just really complicate things. So I'm going to type this in my calculator, so type this all in to find S sub 12. That's something you could do, and this would give me 149. Our next application is more of a financial application. It says Maria and Justin are saving money after college. Maria saved $500 the first year after college and increased the amount she saved 5% each year after that. So we're going to be writing formulas for Maria and Justin. I'm just going to focus on Maria first. So in this problem for Maria, which I'll do in green, the first year she invested $500. The next year she's going to invest 5% more. So my base value is 1.05 because it's increasing. Now we're trying to write a formula or a function here, so I don't have an n value. So Maria's sum formula, it's a sum we can tell because we're adding up her total savings over n years. So how much does she have in the bank for each year? We are not talking about interest or anything here, though. So we have a sub 1 minus a sub 1 times b to the n over 1 minus b. So Justin's function, and just to differentiate them, I could actually call this one m sub n for Maria. I'm going to use a capital because we usually use capitals to denote the sums. So Justin starts also by saving $500, but he saves 5% less each year after that. So same a sub 1, but my b value, since it's 5% less, is going to be 1 minus 0.05, so 0.95. When I write out my formula for him, we'll call it j sub n. We have 500 minus 500 times 0.95 to the n over 1 minus 0.95. So now we're going to use those two functions to answer a question. How much more money has Maria saved than Justin in the first 11 years after college? So we are going to find m sub 11 or j sub 11 and compare them. So plugging in an 11 for n in each of the equations. And as long as you feel comfortable, you can just copy down what I write. But if you want to practice typing in their calculator, these formulas in this lesson are a little complex to type in. You might want to make sure you can type them in correctly. Maria will have invested $7,103.39, and Justin will have invested $4,312. So when I compare them, I'm just going to subtract the two, and she saved $2,791.39 more. So that seems like a lot, but if she's increasing 5% and he's decreasing 5%, the amount they're invested is really, becoming very different over those years, which is why we had such a big number there. So looking at the next page, a lot of financial formulas come from the S sub n formula or some sort of, derivation of it, moving the variables around. Though you just need to know how to apply the S sub n. Any other formula that you need to know how to apply is going to be directly in the problem, kind of like Newton's law of cooling was directly in the problem in the last unit. So that says up here, many financial formulas involve interest or variations of the geometric series formula. Here we are looking at our first one. So I see this kind of complex formula. Now here, I want you to notice that R is the annual interest rate. So this is the R we're used to using. So we're going to leave it as R, where we take a percent and we move the decimal to, and that's R. And that's why we really changed the other one to B, so you can tell the difference between the two. So this problem says you took out a 30-year mortgage. This formula is for mortgage payments for $220,000. The interest rate on the mortgage is 5.2%. So P is still the amount borrowed or the principal, the starting amount of my loan. So we're saying that the person borrowed $220,000. The R is directly the interest rate, so that's 0.052. The 30 years is going to help me find the N, but that is not N. So if I have a 30-year mortgage and I'm making monthly payments, N is going to be equal to 30 times 12, 30 years times 12 months. So I'd have to make 360 payments in that loan. So we are just simply finding monthly payments for this one first, which is pretty straightforward. We're just going to plug the numbers in. It's going to look a little large for our formula, but the calculator can do the work from there. So I'm just plugging in. I plugged in P and R so far. R goes in a bunch of different spots in this formula. 2 to 360. This is definitely something that I'm going to directly type in my calculator and not have to worry too much about PEMDAS or anything. I'm just going to type that in, especially since we have, some advanced features on the graphic calculator for typing it in. So I would type this whole thing in. And that answer would be, just a second, to the nearest dollar, $1,208 for each mortgage payment. So that's our first part. Plug in, pretty simple. Just know how to read the formula and get the numbers in. The next two questions are kind of follow-up questions, and we'll talk a little bit about how mortgages work. So it says, if the buyer makes the minimum payment each month. So if the buyer pays the minimum payment, which is $1,208, on a mortgage, you can always pay more than your payment. And the nice thing about that is you get done paying faster, and also there's less interest that accumulates over time. But all you really have to do, and probably what most people do, is make that monthly payment. So it says, what is the total cost of the mortgage over the length of the loan? So if I pay $1,208 a month, I have to pay that 360 times. So I do times 360. And that's going to give me $434,880. So that's how much you actually pay to pay off the mortgage. Now, the next question, which you should maybe even already be thinking about, is over the 30 years, how much was paid in interest? So this was how much I borrowed, and this is how much I paid back. So to find out how much I paid in interest, that's the difference between those two. So we're going to do 434,880 minus 220,000. Okay. And that is going to equal $214,880 in interest. So that should be a little shocking to you unless you've kind of like seen this topic before. But that 5.2% interest is being put on that amount every single year. Now, as you pay it off, the amount goes down. But in the beginning, you're mostly just paying for interest and a little bit of the cost of the house because the amount is so high. So if we were in class, we might look at that a little more if we had more time. But paying off your mortgage quickly, paying more than the monthly payments really does pay off over time.